Hello everyone, and welcome to recitation number 5. So last time we went over sets pretty heavily. We also went over functions, but we didn't have time to go over cardinality. So today I'm going to solve a couple of questions on functions, then we'll see what this thing is all about. So as usual, you can pause the video to try to solve the problem. But before that, let me just explain what this symbol means. This is ceiling. So the ceiling of a certain number, like let's say 3.5, it's the number greater than or equal to this, the integer number. So this is a real number, 3.5. The ceiling of it is going to be the integer number that's greater than or equal to this. So it's going to be 4 in this case. You can imagine it's kind of like you're in a room. You have 3.5, 3.6, 3.4, a bunch of numbers floating in the air. And at the very top in your ceiling, you have the next integer part. And below on the floor, you have the smallest integer part. So yeah, we have another function which is the floor. So the floor of 3.5 in this case is gonna be just 3. So go ahead, you can pause and try to attempt this problem. Okay. Find the image f of x of each element x here. So f of minus 3. What is it going to be? Just 3 times the ceiling of minus 3 over 2, which is minus 1.5. So it's going to be 3 times minus 1, which is minus 3. Now, in case you guys put it as minus 2, instead of minus 1, no, it's minus 1. Because if we go down a bunch of floors and we reach minus 1, minus 2, and you have minus 1.5 right here, the ceiling, so the integer part that's greater than or equal to minus 1.5 is minus 1. Minus 1 is greater than minus 1.5. What about f of 0? It's gonna be 3 times 0, so it's just 0. Yeah, so the ceiling of 0 is just gonna be 0. If it was 0.000001, the ceiling of that is gonna be 1. F of 5, that's gonna be just 3 times ceiling of 2.5, which is 3. So we have 9 here. Find the pre-images of 9. Well, we already have one, which is 5. They're saying between brackets s, like, is there another one? And yes, we can find another one, which is gonna be 6. So if you write f of 6, it's gonna be 3 times 3 over 6 over 2, it's gonna give you 3. The ceiling of 3 is gonna stay the same, that's 9. So we have 2 numbers giving us the same image. Is the function f an injection, a surjection, a bijection? First of all, is it an injection? Definitely no, because of part 2. We were able to find 5 and 6. 5 and 6 are different, but their images are the same. So it's not an injection. So that should answer part 3 right away. It's definitely not going to be a bijection because bijection requires the function to both be injective and surjective. What about part 2? Is it surjective? That's also gonna be a no, because we have our function going from z to z. And if you notice, the way this function is structured, it's 3 times something. So it's sort of, the best it could be is the multiples of 3, since you have 3 times something. What I'm trying to say, like whatever number you take from this set, when you take it over to that set, it's gonna be some sort of multiple of 3. Well, then everything that's not a multiple of 3 is not gonna have a preimage just because of this. So 2 doesn't have a preimage, 4 doesn't have a preimage, and so on. You can think of a bunch of other numbers. So again, surjective means any number in your image set is gonna have some pre-image here. Okay, moving on. Yeah, and this whole ceiling and floor, they're functions, yeah. So they're in their own way, they're a mapping. So the function ceiling is a mapping that takes you from the set of, let's say, real numbers, like 3.5, radical 2, pi, all that stuff. Takes you from the set R to the set of integers. Okay, by the way, this whole previous thing, it just means these are questions that have come before in an exam. So they're good practices. Okay, you're given here in this question G and F, and you want to consider F from G. So they're going to tell you G has this attribute, F has this one. Prove that F round G has this one. Pause and think about the stuff. Well, the first two are definitely going to be correct because we went into great detail in the previous recitation to prove this. So if F and G are both 1-to-1, F round G is 1-to-1, same for onto. I'm not going to dive into this. If you had a problem with it, you can check the previous recitation. 3 is also easy enough. G and F are both bijective, so they're both going to be 1-to-1 and onto. So you can conclude that F round G is both 1-to-1 and onto because of the first two parts. Then yeah, it is a bijection. So that's kind of like a given. Part 4. If G is 1-to-1 and F is onto, you can't really say anything about F round G. Like it could have the qualities or not. Why? Well, let's draw our sets. We have my A, B, and C. A to B is G, B to C is F. So what are they saying? G is 1-to-1. So we know for any x, y in A, f of x is definitely gonna be different than f of y because G is 1-to-1. But, sorry, this is G of x and G of y. So definitely G of x is gonna be different than G of y since G is 1-to-1. But we have no idea if f is 1-to-1 or not. So for all we know, G of x and G of y could get mapped to the same element. So f of G of x could equal f of G of y. And that makes it not 1-to-1. You can build an example that's structured like this. So f round G is not 1-to-1. what about f being onto, being surjective? Well, if you have some element here in C, using f, it's definitely gonna have a pre-image here. So it's gonna have here, let's say w, such that f of w is z. That's definitely a given. But G is not surjective. So you could have elements here. I ran out of letters, let's say H, that doesn't have a preimage, right? Even W itself, it's not necessary that W has a preimage here. So, and that still makes G and F functions. Remember, what does it mean to be a function? Everything here must point to somewhere over there. W doesn't have anything pointing to it, that's fine. But it makes the whole thing f round G not surjective. Okay. Part 5, you can similarly do an argument like that. Here you can't say loss of generality because it's like a different example. So it's not right to really say that here, because f round G is not necessarily the round operator is not necessarily commutative. So f round G is not the same as G round F. If that was the case, then yeah, you could have said without loss of generality, these two parts are the same. They're similar, but it's not the same proof. What about the last two parts? You can conclude from the previous ones. So G is 1-to-1, F is a bijection. So F is both 1-to-1 and surjective. So you can conclude that the round is 1-to-1 because of the first part. But but now you have to prove that it's not surjective, or not necessarily surjective. Simply by this part 4, you can do that. Like G is 1-to-1, F is onto, that doesn't mean that F round G is onto. So that's done, and you can do something similar for the last part. Moving on. So that's everything. Not everything that has to do with functions, but I think we covered some pretty nice ideas in this and in the previous recitation. Now to move on to cardinality. Well, cardinality here, it's all about, like, we're trying to count. So a set can be finite, or it can be infinite or infinite, however you want to read this. So what does it mean to be finite? Like, if I give you this set right now, let's say 3, 4, pi, you can tell me, hey, this is obviously finite. But if I tell you, hey, how, why, justify it for me, you could go to the trouble of, with your index finger pointing to me, hey, start counting. 3 is 1, then 2, then 3. So you just counted it, it's a finite number. You have 3 elements here. So yeah, it is finite. But what you just did here, it's kind of like you did a bijection, right? This was the set you were trying to prove that is finite. And you made another set, and you're like, hey, 1, 2, 3. It's a finite number. So to prove that a set is finite, then for some number n, for some integer n, or natural number, there is a bijection f that takes you from this set to this set. So like before here, we were able to find the bijection from the set 1, 2, 3 to this set. So it is finite. And your n here is going to be 3. Like, it's a finite number n. Here we said, here it would have been 0, 1, 2 instead of 1, 2, 3. That's okay. It's just like This is a CMPS course, and programmers usually just like to start counting from 0. But 0, 1, 2, it's like the same if you were counting 1, 2, 3. Same thing. Okay. If you can't find such an n, then S is infinite. So, for example, in the set Z of integers, you can't find such an n. You can't tell me, hey, n is 1 million, so there you go, because no, you can even find more numbers. A set can be countable or uncountable. If it is countable, then that means it's either finite or countably infinite. So yeah, there's going to be a difference here. We've already seen what countable means. Before we go into uncountable, let's see what countably infinite means. So, like we just said, a set S is countable if it's finite. Finite, we know what that is. It's just the bijection from this set to the set that you're trying to prove, such that n is some natural number. What about countably infinite? It means there's a bijection from the set n itself to S. So from the set n itself. And we know n starts 0, 1, 2, 3, keeps going. Doesn't really stop. Well, finally, if S is infinite, so like it's not finite, and you can't find such a bijection, then it's not countable. Okay, so really, our definition of uncountable, it simply means it's not countably infinite. So if you can't find this bijection, then it's simply not countable. Okay. Let's see a few examples on this. So we mentioned the set Z of integers is we mentioned it's not finite, right? We know that it's not finite. Now let's prove that it's actually countably infinite. So it's countable. The way I'd like to think of this when I'm trying to prove if something is countably infinite is I try to list them somehow. Because remember, we're gonna try to relate it with the set n. And the set n is just like you're listing 0, 1, 2, 3. It's like you're listing a whole bunch of numbers on one line. Can we do the same for Z? Well, yeah, we can, because obviously that's what we're trying to prove, but we want to try to see the right way to list it. Because if I just start doing the positive numbers, 0, 1, 2, 3, and then hey, after a while, I start counting I start listing the negative numbers, that really won't work because I'll never reach the negative numbers. Because the positives, they don't end, right? 4, 1 million, 1 billion, I'm still gonna be going with the positives, and I never really reach the listing of the negatives. Well, a way to do this is like this. 0, 1, minus 1, 2, minus 2, 3, minus 3. With this idea of listing, if you give me any integer, I'm gonna cross it at a certain point in my list. So if I keep going like this on one line, if you tell me 900 gazillion, jillion, billion, it's gonna be there, and the negative of it is gonna be right next to it. If we do this sort of listing. So yeah, that's how this should give you like a hint whether something is countably infinite or not. Can you find a way to list it on like one line? So for the set Z, we can. But now let's actually try to find that bijection. Because remember, countably infinite, you can find the bijection F from the set N to S. Our S here, it's just Z. Well, let's say we do this. F of N, I'm trying to build my function, my mapping. It's gonna be this. Either just, let's say, minus n over 2 if n is even. Otherwise, if n is odd, I'll say the ceiling of n over 2 if n is odd. Would this work? So we just made a function of a mapping that takes us from the set n to RZ. Will this cover all the possibilities? Well, let's check. So from n to f of n. Well, what happens when n is 0? F of 0 is, well, 0 is even, right? So just minus 0 over 2, it's gonna be 0. So that's fine. 0 gives me 0. Good. What about 1? Well, 1 is odd, so I'm gonna have to divide 1 over 2 and then take the ceiling of that. The ceiling of half is just gonna be 1. So here 1 is gonna take me to 1. So far so good. What about 2? Remember, this is from the set n going all the way to the set Z. Now for 2, well, f of 2, 2 is even, minus 2 over 2 takes me to minus 1. That's what I want. 2 takes me to minus 1. Moving on very quickly, 3 is odd, 3 over 2 is 1.5, the ceiling of that is gonna be 2. So 3 takes me to 2. And if you keep going, 4 is gonna give me minus 2, 5 is this, and so on. So yeah, we build a mapping that sort of works like our list, and it is a bijection, right? Just intuitively, it is. Okay, so that's a way to do it. If you want to go like into the real details, you can try to prove that f is injective and surjective, but this is an obvious one. Like you're not like obviously every number in Z is gonna be represented by some integer here, and no two natural numbers are gonna point to the same element over there. Okay. So Z is countably infinite. What about Q? Well, actually, before we dive into that one, this might seem kind of odd because, well, you have the natural numbers n, and which starts from 0 and keeps going all the way. Then you have Z, which is sort of all that, and on top of it, it's like the negatives of all of those. So it kind of feels like Z should be twice the size of n, but no. Their cardinality is exactly the same. They both have the same size. Because of what we just did, because of the bijection. This is proof. Hey, every element in n is gonna have another element in Z. Like there's no two ways of going around this, you just proved this. Similarly, if you'd like, you can try to do the set of even positive integers, like 0, 2, 4, and 6, 8, keep going. You can try to find a mapping for this, and it's also going to have the same size as both n and z, because this set is countably infinite. What about the set of quotients, so rational numbers? It's also countably infinite. How? Well, first let's try to work with the intuition idea. Can we try to list it in a certain way? Well, they defined it as it's just the rational numbers m over n such that they're both positive. So let's say m is 1, and we see what sort of things work for n. So 1 over 1, 1 over 2, 1 over 3, 1 over 4, keep going. Obviously, if I keep going, it's not going to work because of the same problem that happened with z. If I try to list the positives first and then the negatives, well, I'll never reach the negatives. Same thing here. If I try to list all the rationals that have a numerator of 1 first, I'm never gonna finish. I'm never gonna start with the ones that have, that's for example 2 over 1, 2 over 2, and so on. 2 over 3, 4, da da da. So this line never ends before I start this line. But there's a trick to it. 3 over 2, if I want to list a few more lines, 4 over 1, 4 over 2. And I think you've already know what I'm talking about. It's that whole cross idea or arrow idea. So if we try to list it like sort of the chemistry table of electrons or whatever that we took in school, what does this list look like now? So we're starting with 1 over 1, then 1 over, so yeah, we're going from right to left, 1 over 1, then 1 over 2, 2 over 1, 1 over 2, 2 over 1, then 1 over 3, 2 over 2, 3 over 1. So we're kind of, yeah, we're able now to list them in a way. This is just 2 over 2. We are able to list them kind of like on one line. So now whatever rational number you think of, if it's way down the road here in the third line, there's going to be some arrow that passes through it, and it gets mentioned in my list. Now remember that in sets we don't care about repetition, all of that stuff. So yeah, you might tell me, hey, 1 over 1 is the same as 2 over 2, but that's fine. We ignore repetitions. We only care about the uniqueness. So it's okay if like you repeat your digit twice over here. That's okay. But in the actual mapping that you're gonna make, it's gonna be bijective. So you won't really have done the repetition. Yeah, so that's just an idea of how to deal with quotients. You can expand that idea with, for example, the set, let's say, with the Cartesian product. So R cross, oh no, I don't want to use R yet. Let's say natural numbers cross natural numbers. Is that countably infinite? Can you use maybe this idea to try to do that? Let me know. Okay. So now prove that this range 0, 1 is uncountable. Okay. So this is a new idea. So again, just to recap, we've had sort of 3 ideas so far, including this. If you want to prove that something is finite, you find a bijection from 0 to n minus 1. N is a natural number to your set. Kind of like when we had 1, 2, 3 going to our 3, 4 pi. Or if you want to prove that something is countably infinite, from the set n, you want to find a bijection to your set. So from 0, 1, 2, till forever to your set S. Now we want to prove that, now it's a new idea, prove that something is uncountable. Well, we mentioned uncountable simply means it's not countably infinite. So it's not this thing. Where's my red? It's not this thing. So usually the idea, if you want to prove that something is uncountable, well, assume that it is. So step 1, assume that it is countably infinite, and reach a contradiction or reach a counterexample. Reach something that explodes. So assume that you do have a bijection from the set n to S, and then you want to reach something that's wrong. Okay, before we do that, I just want to mention the idea of overcounting or undercounting. So with this bijection here, we're counting exactly right. You have 3 elements in your set, you did a bijection, and bijection does that. It counts exactly right. 1 goes to 3, 2 goes to 4, 3 goes to pi. Like, it's a bijection. It's exactly right. When you overcount, or let's say in this scenario, I care more about undercounting. Undercounting is like when you have 1, 2, 3, it goes to 3, 4, 5, pi. This could still be a function, but there's no way this is going to be a bijection, because let's say 1 goes to 3, 2 goes to 4, and 3 goes to 5. This is still a function because everything in my pre-image set points to something in my after image, but we are undercounting. We have only 3 elements in the left-hand side, whereas I have 4 elements in my right-hand set. So this is the idea of undercounting, and that's what we're going to do here. We're going to assume that I have a set, that I have a bijection from n to the set 0, 1, and I'm gonna get and I'm gonna reach that I'm undercounting. What does it mean? I have some element here that I actually didn't take care of. I didn't count. Okay, let's start counting. So let's say, hey, 0 goes to 0.0000000001. Then you have 1, right? If we assume that there's a bijection, so let's say here I have 0.000002. If we assume that there's a bijection, then that means we'll have every possible number between 0 and 1 covered. So let's say I have here 0, 1, 2, 3, 5, blah, whatever, and so on. So usually that's how this proof starts. You want to assume that you're able to cover every possible digit. Now this is where it differs. I like to do this proof like this. So how can I find a number that doesn't exist? We'll create a new number such that the first digit in my new number, let's say I'll call it A, it's gonna take something from each of these numbers, right? So this green stuff, we assume that all the numbers have been covered using a bijection. So let's build this number in this way. the first digit of this, so it's 0 point something, the first digit after the decimal part, it's gonna be related to this guy. So here it's, let's call it x0. If x0 is 0, here it's gonna be 1. Then we move on. This one is called x1. It's also a 0, so we'll make it a 1 here. Let's move here. This is x2, and it's a 3. So this 3, we're gonna make it a 0. And we keep going. x3, x4, and so on. So it's kind of like we're moving on a diagonal, and we're picking one digit from each of these listings. If this digit is 0, we'll make it a 1. So if this digit is 0, here we're gonna make it 1. Otherwise, make it 0. So if it's anything else, if it's 1 through 9, then you make it a 0. And you keep going forever. So since these numbers kind of don't end, this guy kind of keeps going with them. Now, why does A doesn't belong here? Well, it's different than every number that's listed here. Why? Well, ask yourself, does A equal this first number? No, because on the first digit, here it's a 0, but here it's a 1. So they're different. Okay, what about the second digit? Does it equal that number? What about the second number? Does it equal it? No, because on the second digit it's a 0. Here it's a 1. What about the third number? No, the third digit is 3, whereas here it's 1. So you can see, as you keep building it this way, it's gonna be different from everyone because it differs each number on a different digit. And the reason we keep moving these digits on the right hand side is that so there's no repetition. Let's take a second actually to try and understand this. Okay, if you want to take a few seconds to pause the video and look at this, because I'm gonna kind of repeat what I just said. So, step 1, remember, our goal is to prove that this is uncountable. So step 1 was to assume that it is countably infinite. So, what does it mean to be countably infinite? It means this: you have a bijection from n to your set that you're trying to prove is countably infinite. What does it mean that that you have this bijection? It means, hey, each element in n is gonna point to each element in this range 0 to 1. So every possible number that you have in this range, it's gonna have something pointing to it. So let z belong to 0, 1. There's gonna be some element here that points to it, such that if this mapping is f, such that f of x equals this z. Okay, so we listed some numbers. Now, ideally, you'd like to make these more general. Like, and I used 0, 0, 0, 0, 0, 1 just to give you a concrete view of it. But usually you'd use variables for this. But that's fine. Continuing with our numbers, we listed all the possibilities, let's say, and that's it. if you think of any z, it's gonna be on this side, and you're gonna have something pointing to it. Well, now here where our contradiction or counter example comes, we're gonna build a number a such that this number belongs to the set. So this a, it's definitely gonna be between 0 and 1 because we were building it 0 point something, but it doesn't have, but it's not in this bijection. Why? We took the first digit from the first element and we changed it. It was 0, and here we made it 1. Then we took the second digit from the second number. It was 0, we made it 1. The third digit of the third number, it wasn't 0, so we made it 0. That's the idea. And you keep going. Now, it's important that if it's not 0, you make it 0, and if it was, you make it 1. Because if you had said, hey, if it's 2, I'll make it another number, it's a 5, I'll make it another number, you might reach, you lose the uniqueness, is what I'm trying to say. That's enough on that. If you have if this doesn't sound clear or you want more explanation, let me know. I'll see if I'll look at it one more time after we do this. So I'm gonna include this link in the description, or you can take it from the slides. This is gonna take us to a website where there's a bunch of truth, false, or multiple choice questions, which is this one right here. You can pause the video and try to solve them on your own, and then we'll do them together right now. So let's see. If A is a countable set and B is uncountable, then the most we can say about A union B is, well, A is countable and B is uncountable. What can we say about A union B? So if you have, let's say A is Z and B is R, because if 0 to 1 is uncountable, then definitely R is going to be uncountable. Well, it's going to be uncountable, right? So the answers might be shifted. Like if I refresh now, I lose my internet. And we're back. Yeah, that was worth it. So yeah, if you refresh, the answers might be shifted. So that's okay. If they're in different order than where you have them. What we care about is if it's green, it's correct. If it's red, it's incorrect. If it's orange, it's partially correct. I hope we run through a couple of these, because this is going to be interesting. It means you're thinking on the right road, but there was kind of maybe a trick. So yeah, we said this was uncountable. Obviously, when you add an uncountable set to your countable set, it's only going to grow larger. If A is countable and B is finite, then the most we can say about A union B is, again, I assume it's going to be countable, right? So you're adding finite. Here in this, I think on this website, they're assuming that finite is different than countable. Remember what we said, countable means either finite or countably infinite. So with these extra links, take them with a grain of salt, okay? So like always, use what you take in class to when you're actually trying to solve an exam or something. Okay, so all the other answers were at, okay. If A is uncountable and B is a finite set, then the most we can say about A union B. I read these without thinking. So we have uncountable and we have finite. Again, so it's gonna be for the bigger thing uncountable. Okay, so far so good. This is obvious, I think. A is finite, B is finite. What can we say about the intersection? Finite. Empty sets are considered finite as well. We mentioned this before, right? Phi, the empty set, it's a set and it's also finite. The size of it is just 0. It doesn't have any elements in it. A is countable, B is uncountable. What can we say about the intersection? Well, we might, I think a lot might have jumped into a conclusion that, hey, it's gonna be the smaller thing, right? So if you have countable and you have uncountable, it's definitely gonna be the thing that's less, which is countable. But no, because remember, you have, let's say, let me just check before talking. Okay, shouldn't have talked. At most countable. Yeah, okay. Yeah, that was right. So I'll explain in a bit what I was thinking. But the answer is yes, at most countable. So what my thoughts were. So what I was thinking is, hey, if I have the set n and then I have the set 0, 1, if they intersect, my first thought was, hey, then it should be 0, 1. So it's still going to be uncountable. But that's wrong because in n you only have the actual number 0 and the actual number 1. You don't have the whole range. So yeah, at most it's going to be countable. You're intersecting. So like all the elements that make it uncountable are going to go away. You're left with what the set you're left with is going to be subset in the countable. But that doesn't necessarily make it countable. Let's move on. If A is finite and B is uncountable, the most we can say about their intersection is, so A is finite, B is uncountable. At most, there's no at most finite, so I'm going to assume it's going to be exactly finite. Okay, so the reason before it would have said at most countable, because what if the sets were completely different? Like actually the example I said before, where if you were intersecting n with the range 0, 1, if 0, 1 was included in that range, then the answer would have been the set 0, 1, which is finite. It wouldn't have been that big thing which is countable, it's simply finite. Or even more so, if 0 and 1 were not included in the range, then the intersection would have been the empty set, which is also finite. But at most, it's uncountable. Again, intersect R with n, you get n, which is countable. At most, it's going to be countable. But with finite, it's definitely just going to be finite. A is countable, B is uncountable. What can we say about the Cartesian product? Interesting. Probably should have tried to solve these before recording. If A is countable and B is uncountable, what can we say about the cross product? I'm going to say uncountable. Okay, good. Makes sense, right? Like on the right hand side, you're going to have uncountably many possibilities. Imagine crossing imagine crossing n with 0, 1, the range 0, 1. Using the same proof, you can say you have 0.0000 something that doesn't exist, that you didn't take care of. If A is non-empty and B is uncountable, then the most we can say about the Cartesian product A cross B is non-empty finite, uncountable. Still gonna be uncountable, even if the left-hand side is finite. Like, even if the left-hand side was just one element A, you're gonna cross it with uncountably many other elements, so it's gonna be uncountable. I'm hoping we stumble across an orange. If A is countable, B is countable, then the most we can say about the Cartesian product is... So is it countable or at most countable? I think that's what we're going for. Yeah. It's still gonna be countable. This is just wrong. I don't think this is gonna be an orange. Yeah. So there's no partially correct if you say at most countable. It has to be countable. If A is uncountable and B is countable, what can we say about A minus B? So this is another way of writing A minus B. It's the elements of A which are not in B, removing the intersection, in other words. So A is uncountable and B is countable. So if you have the set 0, 1 and you remove n from it, where are you? Where are you? I want to say uncountable. Okay. No orange yet. Makes sense, right? The things that makes the set uncountable, you're not removing them. They're still there. If A is countable, B is uncountable, what can we say about the minus? So now it's reversed. The thing you're removing is uncountable. You have the set n, you remove 0, 1, let's say. That makes it still gonna be at least uncountable, right? When I give these examples, they're not rules, they're just examples to kind of like help me think. So if I have the set n and I remove 0, 1, I can conclude from that that at most it's gonna stay countable. Yeah, okay. So I do have an option at most countable, but is it exactly countable? So is it this or this? I'm gonna say the first one, because assume you have n and you remove r from it, then it's gonna be the empty set. You have the set n, you remove r, it's gonna be finite. So at most it's gonna be countable. Saying just countable is gonna be wrong. Okay, we got something. Finite, countable or uncountable? Note that we did not say at any stage B had to be a subset of A. Finite, countable or uncountable? This is what made me conclude it was at most countable. That B didn't have to be a subset of A. Which is why when I removed n from R, I thought, oh, it could be finite. R from n. So yeah, it's not necessarily uncountable. If A is countable and B is countable, most we can say about A minus B, the elements of A which are not in B, we know that. You have countable, you're removing countable from it. Imagine you're removing z, z minus n. It's gonna be now the negatives, which we know is countably infinite. So, or you could be removing n from n. right? They could be the same. So again, at most countable. No orange yet. I'm annoyed that I didn't choose everything. Let me pause and check the rest. Yeah, so far it's all been red. We didn't pass through any oranges. Let A be a set. What does it mean for A to be finite? A is a set. What does it mean for A to be finite? It's not countable. Every element of A is finite. Every element is bounded. A proper subset. There exists a natural n and a bijection from this to this. So, with our definition, it has to do with bijection. There is a bijection from A to a proper set of the natural numbers. So, which one is it? Well, according to our recitation, it should be this one, right? So this is saying, remember, I belongs to n. So we're saying that it's the natural numbers. Then we added a constraint such that I is less than n. So it's kind of like saying 0 till n minus 1. The second one is saying from 0 till n exactly. So the first one is saying it's of size n. The second one is saying it's of size n plus 1. So it should be of size n exactly. Like we're assuming the set has n numbers. Orange. This does not quite work when A is empty. So that's why we say from 0 to n minus 1. So that if it was empty, then you're saying, if you're saying it's of size n plus 1, and then is 0, you're kind of saying you have a bijection from a set that has one element to your A. But A is empty, so that really doesn't work. This doesn't mean that counting 1, 2, 3 is wrong. It's just that counting 0, 1, 2, 3 is wrong. You either count 1, 2, 3 or 0, 1, 2 if your n was 3. Again, if you had 3 elements, you'd either count them 1, 2, 3 or 0, 1, 2. Since the whole world is counting 0, 1, 2 and the programmers as well, might as well just follow them. Let A and B be sets. What does it mean for A and B to have the same cardinality? Let them be sets. What does it mean that they have the same cardinality? If I haven't mentioned this before, this kind of says that we have a bijection between them, right? When you have a bijection between A to B, or it's like you can make a bijection between A to B, then each element over there has an element respectively over here, so that they have the same number. Do we have that? There is a function which is both 1 to 1 and onto. That's like saying there's a bijection. So yeah, that's this one. Onto is not enough. It has to be injective as well. So all the others are not proper definitions. This is the right one. Let A be a set. What does it mean for A to be countable? Let's see how they define it, if it's similar to us. For us, A being countable, it means, hey, it can either be finite or countably infinite. At least that's how I said it in the recitation. A is not finite or empty. That's wrong. This does not exclude the possibility of A being uncountable. So A being not finite or empty, that it could be uncountable, right? It could be R. One can assign a different natural number for each of A. A different natural number for each of A. Still doesn't feel right. A could be finite, right? Exactly. That's the definition of finite, kind of. let me search for the right one. Each element of A is countable. No. What does that even mean? Each element of A is countable. This sounds like it, right? There's a way to assign a natural number to every element of A, such as it's exactly 1, and yeah, we got green, yellow, orange. So this is partially correct. A is of the form A1, A2, A3 for some sequence A1, A2, A3. Why is that not right? Such a set might be finite if the sequence has enough repeats. A is of the form A1, A2, A3 for some sequence A1, A2, A3 if the sequence has enough repeats. This kind of feels like the idea I used in the intuition, that it lets you kind of think if a set is countably infinite, is if you can list it in such a way, A1, A2, A3, da 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 da. But what they're saying is it might be finite if the sequence has enough repetitions. Like, what if this set was A1, A2, A3, A1, A2, A3, A1, A2, A3, and it keeps repeating? Well, it really is just a finite set of 3 elements, because in sets we don't care about repetitions. So yeah, if you want to use the intuition idea that I mentioned before, and I think I did mention that we don't care about repetitions. So in the quotients idea, 2 over 2 was exactly the same thing as 1 over 1. This is actually interesting. Let A be a set. Okay, last two. Let A be a set. What does it mean for A to be uncountable? A contains irrational numbers. Before, I didn't look at this enough. A be a set. What does it mean for A to be uncountable? Okay, so we're just going through the definitions now. So A contains irrational numbers. I don't know if this is like the exact. This is probably gonna be red. It is red, but there's sort of some truth about this. Like usually maybe in specific examples, I don't know if this is general, but usually the things that makes a set uncountable is the irrationals. Because if you think about it, rational numbers, they're uncountable. They're countable, countably infinite. We did it with the quotients, Q. It's when you add those irrationals, radical 2, pi, that stuff, that's when things hit the fan and it becomes uncountable. It's not the complete truth, but it's not even the partial truth because it's not orange, but there's some truth to it. No way to assign a distinct element of A to each natural number. Feels like it. It's not exactly as heartwarming as this one over here. No way to assign a distinct natural number to each element of A. There exists an element of A which cannot be assigned to any natural number at all. This was gonna take me before I read this. A is not countable. Like, this was our definition, right? A is not countable, that's why it's uncountable. But I hope they're not gonna say then it could be finite. This does not exclude the possibility that A is finite. In my definition it does. In their definition it does not. So A could be finite. Fine, is it D? No. Keep going. There is a bijection F from A to the real numbers R. This feels nice. Orange. The real numbers are one type of uncountable set, but it turns out there are other uncountable sets of different cardinality than R. That's actually true. Yeah, I was taken away from this. So if you've watched the movie The Fault in Our Stars, and there's a line where they say there are different sizes of infinities, or some infinities are bigger than others. Yeah, actually spot on. That's actually true. Some infinities are bigger than others. What do I have left? B, C, and G. There is no way to assign... Okay. I think this is what I liked at first, but it wasn't. Or was it this? A distinct element of A. There's no bijection of F to the natural numbers. Ah, okay, it's G. Like, this is our actual definition of not countable. Or not. This does not exclude the possibility that A is finite. Fair enough. Back to B and C, which sound very similar, that I actually want to focus on this a lot. There is no way to assign a distinct element of A to each natural number. There is no way to assign a distinct natural number to each element of A. To assign a distinct element of A. They sound so similar. So here I think they're saying on the right hand side you couldn't find, and I'm gonna go with B. Okay, I seriously went through each element and none of them was right. This is only true if A is finite. To be fair, all the things that I thought were the answer, they kept saying, hey, it's not, A could be finite. But in my definition, there's no way to assign a distinct natural number to each element of A. Distinct natural number to each element of A. Okay, sure. So that's how they've assumed that A is uncountable. Took way too much time on this. Let A be a set and B be a proper subset of A, so that B is not equal to A. So A is a set, B is a proper subset, so it's strictly a subset in A. There's no possibility that it could be equal to A. Is it possible for B to have the same cardinality as A? So A is a set, B is a proper subset. Is it possible? Yeah, definitely. It's possible because, hey, N and Z. N is a proper subset in Z because all the elements in N are definitely gonna be in Z, but -1 is not in N, for example. But they have the same cardinality. So we're only gonna look on yes. Yes, it's possible for any A. Yeah. Only if it's countable, infinite, or uncountable. Some definitions that we might not have been used to. So in my example, when I was thinking about N and Z, those were countable. But what about if it was infinite? So here I think infinite here means both this and this. So it works for countable. Then that means this choice C is gonna be wrong, because infinite means both countable and uncountable. So if it does work for countable, by the example I just gave, then it could also work for uncountable, but that doesn't mean it doesn't work for countable. So this or this or this. Well, it's not going to be the last one, because for finite it won't work. If you have set of size 5 and set of size 3, and the 3 is a proper subset of 5, not the same cardinality. So our last question would be, would it work for uncountable? Oh, sorry, yeah, would it work for, it works for countable, does it also work for uncountable? So if I have the set R, I think the set R and the set 0 to 1, the range, I think they both have the same size. So yeah, it should work for uncountable. So yeah, it works for infinite, which means both countable and uncountable. The set R should have the same size as the set 0 to 1. Any yellow? Okay, good. Not bad. Not bad. Okay. So this was the only thing that I didn't quite 100% understand, because this is where like the clash of definitions happen. So again, rely on the definitions you take in class, because it might differ slightly. Like as a big image, we kind of understand what they're saying, but in the small details, it might differ from one uni to another, from one website to another. So it's in those small details where you rely on what you take in class. If A is a set, what does it mean to be uncountable? No way to assign a distinct natural number for each element of A. Sure. Okay. I really hope you try to do this on your own, because it would have been very helpful. As you can see from my own challenge while walking through this, like they're not just, hey, choose the answer and you're done. It has a lot of thinking to it. And even, hey, you might have partially got the answer correct. That's kind of a nice way. Like it's nice when you get the partial answer, because there might be a slight idea that you don't understand 100% and now you do. Like with this thing, for example. Not this. Okay. I think that's enough for now. So if you have any questions, as usual, please use the forums. And yeah, see you on Monday or in the next one.